stars, they have too dense spectra, too many molecular lines, often not understood, not predicted correctly by theory, because it's incredibly difficult to calculate positions and intensities of molecular lines. And these stars are also faint. So we are talking about objects fainter than 10th magnitude. It's difficult to obtain high precision polarimetry for such stars. There is an interesting feature of M dwarfs that in the middle of this spectral type, around M3, M4, at this mass, 0.35 solar masses, the interior structure of these stars changes. So above this mass, the interior structure is kind of similar to the Sun. Outer part of the star is convective, and the inner part contains radiative core. But below this mass, the stars are fully convective. The entire star has convection zone, and what it means is that there is no tachocline. There is no this shear layer where, as we know from the Sun, magnetic field is probably generated. So the dynamo in these stars is definitely of non-solid type. And similar to solid type stars, these stars also show proxy indicators of the presence of the field, again, X-ray emission, chromospheric line emission, and so on. It's only around the end of 90s, middle of 90s, where first direct evidence of the presence of magnetic field in active M dwarf stars appeared. And you see, one example here, I think that's a conference proceedings paper with a nice plot, but the actual discovery was published in 96, I think, for EVLAC, which is well-known red dwarf active star. So what these authors did, they looked at near-infrared spectral region containing iron line with large lambda factor. So this iron line has lambda factor 3, which is quite a lot. So this is iron line, and other spectral features which surround this line are produced by titanium oxide molecule, which in this particular spectral interval is not magnetically sensitive. And so what you see here is the sequence of M dwarf spectra for inactive M dwarfs, these color lines. And these M dwarfs different in spectral type, so they are different in effective temperature, presumably. And you can see as we go to later spectral types, the depth of the molecular features increases, as one would expect. And then there is this black line corresponding to active M dwarf, EVLAC. And you can see that, the molecular part of the spectrum of EVLAC is more or less corresponding to the temperature sequence of inactive stars. But the iron line looks very different. And this distortion is exactly what one expects if the line starts to split into the triplet. So you start seeing partially resolved sigma components on both sides of the line. Here the picture is not so clear because there is this blending with titanium oxide all over. But nevertheless, these authors have managed to measure magnetic field of this star, so the average magnetic field, which for these stars is expressed as a product of B times F. So F is the filling factor, and B is magnetic field strength. So it's roughly 4 kilogauss to explain this spectrum. What filling factor means is the fraction of the surface covered with this field strength. So in principle, that star can have, say, 8 kilogauss field covering 50%, or 4 kilogauss field covering 100% of the surface. And to some extent, it's not so easy to distinguish these different scenarios. But maybe 8 kilogauss would be distinguishable, but you can make fields slightly stronger and decrease F and get the same spectrum. So this is why in this business people often express their results as a product of the field strength and the filling factor. And this is another example from our own study with the ISO-VLT Criris instrument. So some spectrograph looking very far in the, no, not very far, in the near infrared, in the K band. And Zeeman effect, remember, grows as lambda squared. So even lines without very large lambda factor would show splitting for the field around 4 kilogauss. And you do see a nice splitting in this case it's a sodium line, also in the one of the active M dwarf stars, YZCMI. Okay, so apparently fields at the order of 1 to 4 kilogauss exist in these M dwarf stars, and they can be found through the investigation of Zeeman effect in stock size spectra, magnetic broadening and splitting of spectral lines. There has been a very productive line of research related to M dwarf and also to brown dwarf stars, exploiting this way of measuring field through the Zeeman broadening of stock size spectra and using the lines of this molecule, iron hydride. So it turns out that, well, in general, molecular spectra are very rarely Zeeman sensitive. So quite often we see no effect in molecular lines, but this particular molecule in this region is producing a lot of spectral lines with large Zeeman splitting. And for instance, in the sun, the top is the spectrum of the sunspot in this region. And you see this funny distorted shapes, which are all due to splitting of molecular lines due to Zeeman effect. Some of these lines are not magnetically sensitive, and then they look very sharp, like these two. So you can clearly see that by comparing magnetically sensitive ones and insensitive ones, we can determine the field. And this is example of two M dwarf stars in the same wavelength region. And again, the black line is star without evidence of magnetic activity, and the red one is the star with activity. You can see that the magnetically insensitive lines are nicely matched, but there is a lot of difference in lines affected by magnetic field. So that's how this molecule is helping us to deduce the presence of the field and measure it. And this author is Ansgar Reiners, Gibor Basri. They have done lots and lots of measurements in low mass stars using iron hydride and near-infrared observations taken at different telescopes. One has to use 8 10-meter class telescopes to study these faint stars. And the method that they have used is incredibly simple, so it's really at the level of any student can do. So what they do, they have 2 stars. One is inactive, another is active. And for active star, somebody else has measured the field. Well, actually, the active standard is precisely this star, Ivilak. And then they just linearly interpolate between these 2 template spectra to match observations of individual stars. And they also add a little bit broadening to match the different rotational velocities, different rotational broadening of the spectrum. So using this method, they have analyzed maybe about 50, 60 late M dwarfs and brown dwarfs, and found field for some of them. Well, examples are shown here. So the observations is the histogram, the best fit model, and model here is just the addition of these 2 templates with different weights, is the green spectrum here, and then the blue one is non-magnetic template, and the red one is magnetic template. So you see that some lines are very sensitive to magnetic field. And this is an overview of their results. A magnetic field here, or rather they are plotting magnetic flux density, so B times F, is plotted as a function of Rossby number, so it's, remember, rotation period divided by convective turnover timescale. And their stars are here, late M dwarfs, these red symbols. So you see they have around kilogauss, maybe 2 kilogauss, maybe 3 kilogauss field. And really the sensitivity of this method is not very high. You can imagine it's not detailed spectrum synthesis, so you probably don't detect fields of a few hundred Gauss. So I would actually be a bit doubtful about this point. And they compare their field measurements with similar measurements for sun-like stars. So for sun-like stars, there is this increase of magnetic field strength with the decrease of the period. The faster the star rotates, the more magnetic field is generated, while all late M dwarfs are sitting on this saturated regime. Well, it's not even clear if they belong to this sequence. Maybe they are forming another sequence parallel to the one for solar-type stars. This is another picture where they are correlating magnetic field strength on the x-axis with H-alpha luminosity on the y-axis. Maybe there is a loose correlation here. And you can also see here different spectral types. So somewhere here we have transition to brown dwarfs already. So a lot of measurements are available, and I should emphasize that there is very nice review of measurements of fields in low mass stars by Ansgar Reiners in Living Reviews in Solar Physics, which is online, free online journal. There has been efforts to analyze iron hydride spectral lines with better models, with spectrum synthesis models and real model atmospheres of the stars. In particular, this is the paper currently almost accepted. And what these authors did is matching individual iron hydride lines with not just B times F, but some distribution. They tried to infer distribution of different magnetic field strength. So it's not deriving geometry, but it's statistically trying to figure out how much of, say, 3 kilogauss or 2 kilogauss field is present on the surface. And, well, observations are shown with dots, best fitting model with red line, non-magnetic model dashed line, and this blue line, which is showing up here and there, is the spectrum with a single value of magnetic field. So if you take this field value and assume that the entire surface of the star is covered with a single value, then you obtain blue line. So you can see that the blue line is worse than the red line. So you really need some distribution of the field strength to describe observations, and this is distribution that they get, for instance. I guess the most important outcome of this study is the necessity to introduce large fields for a small fraction of stellar surface. So they claim that some 20% or so of the surface really has fields as strong as maybe 5 or 6 kilogauss, which would be significantly larger than equipartition field strength for these stars. So for these stars, equipartition is around 3-4 kilogauss. So a result that requires some theoretical thought. There has been a parallel work on M dwarfs trying to derive magnetic field geometries for these stars using Zeeman Doppler imaging. And quite incredibly, these stars turn to be very good targets for looking at Stokes V profiles. And very differently from solar-type stars, which tend to have complicated Stokes V profiles, low amplitudes, M dwarfs, active M dwarfs, have simple profiles. So we are back in the regime where the field is like in A stars, roughly dipolar, and in fact very often nearly axisymmetric. So this is example of magnetic field reconstruction. This is the fit to observations, and this is reconstruction. You see a polar projection, you see a radial azimuthal meridional field, and it goes up to 2 kilogauss here. And you see two different epochs. And the maps are fairly similar. You can say that maybe there is some additional rotation between these two maps, but this could be simply due to inaccurate rotation period of the star. But there is a little problem, and the problem is that actually these authors, they need to reproduce TOXV spectra, they also need additional filling factor. So this 2 kilogauss field, they also multiply by some filling factor. Don't ask me what this means physically. But at the end, the field that they infer from TOXV is just 0.6 kilogauss, whereas for the very same star, it's again the CVLAC, we have 3.9 kilogauss average field from STOXI. So there is this systematic, and for other stars, this difference is observed as well. So broadening and splitting of STOXI gives much higher field than interpreting polarization in STOXV. So this star is actually unusual in showing a lot of variability in STOXV and non-axisymmetric field. The more typical situation is actually like that. So the field is almost axisymmetric, little variability in STOXV, but still you see very clear signatures. And still this discrepancy between mean field inferred from V and from I. This is an interesting plot. This is an overview of different properties of magnetic fields, magnetic field maps determined with ZDI as a function of stellar mass and the stellar rotation period. Okay, so M dwarfs are here, solar type stars are here, and there are some intermediate masses over here. This dashed line shows the limit when the star becomes fully convective. The size of the symbols is proportional to the field strength, to the average field strength, or I think actually it's proportional to B squared, so to energy of the field. The color is reporting contribution of poloidal and toroidal field. So reddish symbols is when poloidal field is dominating, and this green is when toroidal field is dominating, and the shape corresponds to axisymmetric versus non-axisymmetric field. So when the shape is more round, it means that the field is kind of axisymmetric with respect to rotation axis of the star. So this is an overview of what Zeeman Doppler imaging maps for stars, starting roughly from solar parameters down to M dwarf regime, what Zeeman Doppler imaging tells us. And you see there is some systematic trends. So some poloidal fields for solar type stars, the rise of non-axisymmetric toroidal fields, and then the very strong poloidal axisymmetric fields in M dwarfs. However, for M dwarfs, actually the picture is not so clear because there are also stars with very similar parameters having completely different geometry and strength of the field. So it's clearly not just a function of mass and rotation period. There is ongoing debate on this discrepancy between STOXV and STOXI results. So one suggestion, so this is comparison of average field derived from STOXI and STOXV. I think here STOXV energy, magnetic energy, is divided by STOXI energy, and this is expressed in percent. So STOXV sees few percent of the total magnetic energy. And one interpretation of this is that, in fact, the star might have a very complex field, small-scale field, in addition to the global large-scale field. So there is some weird power spectrum, and the STOXI is sensitive to the small-scale fields, while the small-scale field is not seen in Stokes V because of cancellation of different field polarities. What does theory tells us? Well, there has been several attempts to generate magnetic fields in fully convective stars, and apparently it's very easy to do that. And yes, indeed, some studies obtained these kind of pictures with roughly global boloidal axisymmetric field with a strength similar to equipartition. There has been even recent study which pointed out possibility for the convective dynamo to operate in two regimes, and for the same star to jump from one regime to another regime. And in one regime, axisymmetric strong field is generated, and in another regime, non-axisymmetric weaker field is generated. So this might explain the stars here, the same parameters but very different field. There has been also a very interesting suggestion in this paper, which is actually a Nature paper, that turbulent dynamo operates in some kind of universal way over many orders of magnitude from the cores of rocky planets to M-dwarf stars. So these authors, they have carried out a sequence of numerical models for these different environments, and they found that every time for every set of parameters, it's the same fraction of convective energy, convective heat flux, that goes into the magnetic field. So then in log-log plot of field strength versus some stellar parameter, there is this linear relation. And if one plots measured magnetic field of Earth, Jupiter, and then the stars which have saturated dynamos, so stars rotating fast enough, and they nicely fall on this line over many orders of magnitude. And this also predicts then that the strength of several hundred Gauss for brown dwarfs. There is also an ongoing discussion about possibility for magnetic fields to change the structure of low-mass stars. And probably that's the only place on the chart diagram where this can be clearly observed. So there has been ongoing problem that if one computes theoretical radii for stars, low-mass stars, and tries to compare this theoretical radii with the radii measured empirically using eclipsing binaries. So you know that in eclipsing binaries, one can determine masses and radii completely without reference to theoretical models. And then if one plots radius versus mass, so the predictions of theory are going with this solid line, and then measurements of radii show larger than expected radii. And it's very difficult to attribute this discrepancy to some problems with the input of theoretical models. So there has been a suggestion that all these stars are magnetically active, and that's logical because, okay, they are enclosed binary systems. So they're tidally locked and they have magnetic field generation. So then in M dwarfs, magnetic field changes the radius. It inflates M dwarfs. And there has been a study by several people, in particular this group has managed to reproduce some of these observations by introducing magnetic field into the structure, into the calculation of interior stellar structure. And well, the point here is that these are the two components of some M-dwarf binary. I think these two, YY Geminorum. And then this is the age of the star determined because it's member of cluster, or moving group rather. This is the measurement of the radii coming from studying eclipses in this system. And then prediction of theoretical model without field is the solid line, and with magnetic field is dashed line if they assume this kind of field on the surface, which is quite reasonable. It's not excessive, 0.7 kilogauss. So there is this possibility, the only place in the HR diagram where it seems to be realized. Change of stellar interior structure by the magnetic field. Now, as one of the last parts of my overview of what's happening on the HR diagram, I'd like to mention young stars. And here I consider the entire range from M-dwarf masses to maybe intermediate mass stars, because at the pre-main sequence evolutionary tracks, and this is what is shown here, pre-main sequence tracks, these stars look more or less the same. These are T-Tauri stars. And, okay, all of them initially are fully convective. So here, when they form, they're fully convective. And then they go, after some evolution, they go into the situation when only outer envelope is convective. Magnetic field for these stars is like really this elephant that is destroying everything, but also is responsible for lots of theoretical models require magnetic field for these stars. So they have to get rid somehow of their angular momentum with which they are formed. So magnetic field is believed to play a major role in angular momentum loss in these stars. These stars accrete material from protostellar disks, and this accretion is guided by the magnetic field. It is believed to be controlled by the magnetic field. We are talking about magnetospheric accretion. The geometry of the disk, and in particular its truncation, so this doesn't go all the way to the star, it stops somewhere, is again determined by the magnetic field. And this somehow also has impact on planetary formation. Things like migration of giant Jupiter-sized planets inwards is stopped at the place where the disk is truncated. So magnetic field is really a big elephant in this business. But not so much observations of direct observations of magnetic fields was done until recently. The observational picture is a little bit similar to M-dwarfs in the sense that we have broadening measurements from StoxI, and we have spectropolarimetric measurements giving us maps, ZDI maps, and there is also discrepancies often, so different field strength from different observables. Well, this is the typical example of T-Tauri star with the evidence of magnetic field in Zeeman broadening. So these are K-band infrared spectra, and these are the spectra of magnetically insensitive lines, CO band. You see these narrow, sharp lines, and these are several titanium lines with large lambda factors. And the best fitting model with this kind of field distribution is this thick line, and then thin line shows the non-magnetic model. And this author, Christopher John Skrull, is the main person doing this kind of work, and he measured a lot of stars. And surprisingly, well, they have this kind of fields, 1, 2, 3 kilogauss are quite common, but surprisingly, these field strengths have not been found to correlate with any other properties of the stars. In particular, these stars have measured accretion rates, and magnetospheric accretion models can be used to predict what should be the magnetic field strength. And this is comparison of predicted versus observed. So they should line up along this straight line, and they don't, so it's not really understood why. And yes, spectropolarimetry is also becoming possible for these stars. Again, we are talking about heavily obscured 11th, 12th magnitude objects, so we can only use largest telescopes, maybe 4-meter class telescopes to observe these kind of stars. And, well, using the standard technique applied in late type star business, least squares deconvolution, one can see Stokes V signatures in photospheric spectral lines. One can see Stokes V signatures in the emission lines, like calcium infrared triplet, emission lines formed in the stellar chromosphere, and very puzzling observation, which is, we find this for almost all T Tauri stars, that emission lines due to helium, which presumably trace the accretion funnels. So emission lines are formed where accretion flows hit the surface of the star. For some reason, emission lines of helium are showing enormous longitudinal fields. They show enormous signals, which look like Zeeman signals, and they show fields like 4 or 5 kilogauss. And this is example of detection of this field, and so this is Stokes V, and this is right and left circular polarized spectra, something we actually measure on the detector, and you clearly see shift between them. So how this huge field can be compatible with lower fields seen in other observables is a mystery at the moment. Well, a few words about Zeeman Doppler imaging results. Basically, there is ongoing project, large program devoted to mapping magnetic fields in T Tauri stars, led by this guy, Jean-François Donati. He's using Espadon spectropolarimeter and systematically observing T Tauri stars with different masses. And what they find is that roughly all their maps of magnetic fields in T Tauri stars are representing two classes of maps. So in one class, which is shown here, they see magnetic fields which are more or less axisymmetric and which are represented by different combinations of dipole and axisymmetric octopole. So this is radial component for 4 stars, and you see polar projection. So we see the stuff from the pole. So this would be a purely dipolar field, and this is octopole-dominated field, and various possibilities of different combinations. So axisymmetric field. But another half of their targets show much more complex field with non-axisymmetric contributions and also smaller field strength. So if you look carefully, you probably don't see this scale, but the maximum here is like 400 Gauss. Well, here it's 1 kilogauss, 500, and here it was several thousand Gauss, so 2 kilogauss all the way. So there is these two classes of T Tauri stars. And it turns out that they can be very nicely traced to different places in the pre-main sequence evolutionary tracks. So these are, again, the pre-main sequence evolutionary tracks, and different colors here correspond to different internal structure of the star. So in here, the stars are mostly convective, fully convective, and here they have radiative cores. And it turns out that stars with global axisymmetric fields are found here, and with the more complex non-axisymmetric fields are found in this region. And yeah, this situation is then very similar to what we've seen when comparing M dwarfs and solar type stars. So fully convective stars have global axisymmetric fields. Partially convective ones have more complex non-axisymmetric fields. These models of magnetic fields reconstructed from time series of Stokes V observations have now starting to have a large impact on magnetospheric models which try to figure out how exactly accretion process occurs on young stars. So before, magnetic field was, as I said, very important, but before we had pictures like this one, so just dipolar field aligned with the stellar rotation axis, very simple, very axisymmetric. More recent works, in particular by the group led by Romanova and collaborators, they started to actually to incorporate real magnetic field maps and compute 3D models of magnetospheric accretion. So in this case, they are computing model for oblique dipole, still rather simple geometry, but you see that even this deviation from axisymmetry leads to some interesting phenomena, like instead of rings where accretion ends, they have some spots. And this can be compared with observations. And in a more recent studies, they actually took real maps of T Tauri stars and tried to produce 3D models of accretion based on these maps. And this is example of such calculation where you see this bright spots. This is places where accretion streams are ending on the surface of the star. So the bottom line and conclusion is that it's important in the context of understanding magnetospheric accretion, it's important to know exactly what is geometry of stellar magnetic fields. It actually has some influence on the accretion rates of these stars. If we look in what is going on in the forefront of this business of investigating magnetic fields of young objects, the things that really pushing the limits are attempts to detect magnetic fields at even early evolutionary stage. So T Tauri stars are so-called class 1 young objects, so stars which are already seen. They are not obscured very much, and they have disk, and one can try to check what's going on even earlier in the partially obscured class 0 objects. And there has been one report of detecting magnetic field in one of those stars. Well, this detection, which you can see that this is based on very noisy spectra because it's I don't know, 15th, 14th magnitude star. So even I think these are Keck data. Even Keck doesn't allow to get good spectrum. And then another interesting possibility is to study magnetic interaction between the star and the disk by also probing the field in the disk itself. So in the disk, we could have different mechanisms of magnetic field generation. And there has been one paper claiming the discovery of magnetic field in the disk. And this is a special type of T Tauri star with a lot of activity in the disk, very powerful accreting flows, so the disk is bright relative to the star. So that's why it was possible to see contribution from the disk in the stellar spectra. And well, this contribution apparently shows some Stokes V profile corresponding to kilogauss field. So in the future, when we get better telescopes and larger mirrors, maybe 40-meter telescope, we could possibly study both the field of the star itself and the magnetic field inside the disk. Now, I will, in the final 15 minutes, I will depart from the main sequence and say just a few words about white dwarfs and giant stars. So for the giant stars, the investigations are basically going on, trying to detect fields going on the last few years, 2 or 3 years only. And there is no coherent picture so far, but it is possible to detect magnetic fields in high mass giants. So this is example of such detections. What you see are least squares deconvolved profiles. So these are Stokes V signatures indicating presence of the field. And you see a theoretical HR diagram for the evolutionary tracks of 5, 9, and 20 solar mass stars. So in massive evolved stars, there are some field detections. And this is corresponding plot for the giants which evolved from low mass stars, intermediate mass stars. You also see some detections plotted on the theoretical HR diagram. What is interesting is I think this plot, it tries to compare maximum longitudinal field with VSI, no correlation. But from this you can figure out that the typical field strengths are extremely small in these giant stars. We are talking about from 1 Gauss to maybe 5, 6 Gauss. So the only reason that we can detect these fields is because many giants are bright, so it's possible to get very high signal-to-noise ratio spectra, and because giants have a lot of lines that can be combined in this least squares deconvolution method. An interesting thing that was also discovered is that some giants show very different type of field compared to other giants. So majority of giants show weak fields which evolve, which tend to be complex, so showing similar pattern of behavior as solar type stars would show on the main sequence. But there are now 3 or 4, maybe 5 giants which show quite strong magnetic field and very slow rotation, and magnetic field is nearly dipole axisymmetric. So you see example of such giant here. This is magnetic map derived from Stokes V, with the fit to Stokes V, and the position of this giant on the HR diagram. And one can see that this giant has evolved from a star with a mass around 2 solar mass. So this is the range where magnetic A stars are found. So apparently, and that's the leading hypothesis in explaining these stars, that some stars manage to retain their global dipolar field even when they become giants. And this field survives for some time and showing up in the giants even though they have convective envelopes. So convection in the presence of dipolar field, global dipolar field. And then magnetic white dwarfs. They are quite different beasts compared to all stars considered until now. Their magnetic incidence is a little bit unclear, but again, one usually talks about 10%. And their fields span a very large range, up to 10 to the 9 Gauss. The lower limit here is a bit uncertain, so previously a lot of studies focused on studying strongly magnetic white dwarfs, but now with the better telescopes, better equipment, recent studies turned to stars, white dwarfs with a lower magnetic field strength, and also finding very many of them and about a 10% incidence. Their phenomenology is quite similar to AP stars. They seem to have stable fields with dominant global component, often dipolar, and they also have this oblique rotator phenomenology. So the star rotates, field is oblique, and we see different projection of the magnetic field. Where this field is coming from is not clear. A very popular hypothesis that this field is actually coming from AP stars. You see very similar incidence, 10%. And if you try to estimate what should be the field strength for white dwarfs, assuming flux conservation. So assuming that if the star is compressed, the entire magnetic field is frozen in and compresses together with the star, which may be not such a good assumption after all, but nevertheless, AP stars would then produce the strongly magnetic white dwarfs. So this number actually is matching roughly the few kilogauss field of AP star. Where this weak field magnetic white dwarfs come from, it's not clear. Maybe it's telling us that A stars also have fields at this 1 Gauss level that is seen in Vega. Another possibility is that magnetic field is generated by merger events. The methods of magnetic field detection for white dwarfs are more diverse than for main sequence stars, simply because they span so a broad range in magnetic field strength. So we go from looking at the same Zeeman effect as I described for other stars, so looking at Zeeman splitting of spectral lines, looking at the Stokes V signals in individual spectral lines, to something completely different, like in this range, the quadratic Zeeman effect starts to dominate, and instead of individual lines, we see kind of smeared spectra. And for fields above 10 megagauss, we start getting continuum polarization, and the spectra becomes completely unrecognizable. The Zeeman shifts of spectral lines are thousands of angstroms, and in fact, we are in the regime where Hamiltonian has to be, well, magnetic field is no longer a small perturbation to Hamiltonian of an electron in an atom. So the entire spectrum of the star, the entire atom, has to be considered in complete quantum mechanical calculations with magnetic field. So it's not like each line is nicely splitting into Zeeman components. And this is an illustration of such strong field white dwarf. So we see some spectrum, and we see some broad features, and we see some sharp features. And I think this is helium rich, a helium white dwarf. And if one does these complex calculations for the helium spectrum in the magnetic field, so this is strength of the field, this is wavelength, and position of individual Zeeman components is shown with these lines. So you see there is no linear behavior anymore. They are doing whatever they want. But the interesting tendency is that at some, they often change direction. So first component shifts this way, and then after a certain critical field strength, it shifts another way. And what this means is that if magnetic field of the star happens to be here, the scatter of the field over the visible surface will not distort the component very much. So if for instance, field is somewhere here, then part of the surface has one field, another part has another field, so the spectrum is very smeared because of different shifts. But here the spectrum would not be smeared because change in field strength does not correspond to large shift of Zeeman component. So there is this concept of stationary Zeeman components, and presumably these narrow features correspond to such stationary Zeeman components. And this is how magnetic field is roughly measured in strongly magnetic white dwarfs. That's one of the methods. So for this, I think for this white dwarf, the authors say that roughly here is the field strength. So this bending would produce stationary components. Whereas for weak field, or in quotes weak field, 165 kilogauss, we still see familiar things like, okay, in this case we have calcium infrared triplet lines split into Zeeman patterns, and we have Stokes V signals. There have been also studies similar to Zeeman Doppler imaging for white dwarfs, and this is an example of one such study where they tried to reproduce both Stokes I spectrum and Stokes V spectrum, and this is the geometry, and in this case geometry is given by the field strength, so this is field strength, and this is cosine of the angle between line of sight and the field. And this is some map indicating how far the open field lines are going from the star. So you see that the field topology is not dramatically different from what we have among A stars. So something that looks like dipole, or maybe distorted dipole, maybe dipole plus quadrupole. And, well, as a very last thing that I'd like to mention is that another interesting place where magnetic field in white dwarfs is being considered is magnetism of cataclysmic variables, and some fraction of them have white dwarfs with magnetic fields. So we have white dwarf, and we have a dwarf star which loses its mass, and white dwarf accretes and maybe displace some dwarf nova events. So there are really thermonuclear explosions, and that could be also a situation for type 1a supernova, of course. So this is basically it for my overview of magnetism on the HR diagram. And you have asked some questions. You're welcome to ask more. So I will be here today and leaving tomorrow. And it was a real pleasure, and thank you for inviting me. So if maybe there are some questions, no? Everything was clear? Okay. Good. Yeah, we need to leave some time to change computers. Okay.